Okay, this is section 3.5. So what we're going to talk about is velocities and two different velocities. So on your salmon sheet, you're going to look and see that there are, under the formulas that we are actually to the left of the formulas for arc length and area of a sector, we have angular velocity and linear velocity. These are the two essential components of this section. They're not necessarily simple. I'm going to do the what I think is the easier one first and the harder one second, and then at the end of the day, if you are totally lost, that's fine. We're going to work 2-3 days in class working through these types of problems. So give me your best effort, and then we'll kind of fill in the gaps once we get to class. So if I give you this specific question, so I'm going to start with just a question. Okay, a Ferris wheel has a trip around the wheel, took 20 minutes. So if it actually takes you 20 minutes to get all the way around, which, oh my goodness, that'd take forever. How fast were you actually traveling around the wheel? So if you imagine yourself, all of us I'm sure has been on a Ferris wheel, you in that cart, how fast are you physically moving as you go around the circle? There are two different ways that you could actually answer this question. The first one is called linear velocity. Think linear, a straight line, how fast you're going. Miles per hour, feet per second, feet per minute, feet per hour, anywhere. It's a distance over a unit of time. Okay? So distance over a unit of time is how linear velocity is calculated. I think this is the more difficult one. I'm going to do this second because there's just so many different ways that you could go about doing it. What I feel is the easier one is what we call angular velocity. So this is another way that you can figure out how fast you're actually traveling. Okay? Angular velocity gives the amount of the central angle. Okay? So your theta, or your angle, that's the idea of angular velocity. It's the amount of the central angle over a given period of time. So in either case, you're going to have time on the bottom, but angular velocity gives the theta, or your central angle. So what I want to kind of talk about is more angular velocity first. Okay? So in the original statement about the wheel, or the Ferris wheel, going one full rotation in 20 minutes, I would like to know what the angular velocity is in radians per minute. So we got to think about how angular velocity, which is denoted with an omega, it kind of looks like a small w, but we call it omega, is called the theta over time. So if you actually look at angular velocity formula on your salmon sheet, this is what you're going to see right here. And what you need to figure out for each individual problem, can you figure out the angle that you actually traveled in radians? Now once again, theta is in radians. That's been the same way all chapter long. Can you figure out how many radians we traveled? Well, one full rotation. If you think about a Ferris wheel, one full rotation starting at the bottom, going all the way up and all the way back around, one full circle, okay, is 2 pi. We learned that way back in section 2. So as long as we know that 2 pi goes all the way around, that's the amount of radians the person actually traveled. Well, how long? Unit of time, it doesn't matter how it's stated. Okay, I gave you 20 minutes, so that's actually how fast you're going. And then what you got to do is kind of look at the problem and see, are they actually asking for the same unit of measurement? Since I'm asking for a minute and I gave it in minutes, you're done. This is pretty easy. So I have 2 pi over 20 minutes, and usually you want to reduce as much as possible. 2 goes into both of them. So pi over 10 radians per minute, or the radian is the measure on top, the minutes is the label on the bottom. So there's the answer. That's as simple as it has to be, but that's because I gave it to you in pretty simple terms. Okay? So I gave you 2 pi over 20, which reduces to pi over 10 radians per minute. What happens if I gave you a different problem? Using the same scenario, angular velocity in radians per second. We already know what it is in radians per minute. I know it's pi radians over 10 minutes. That's just taking my other answer. If I want seconds on the bottom instead, now radians per just means divided by seconds on the bottom. I now need to go from minutes to seconds. We need a conversion factor. Do I have a relationship? Everybody should be like, sweet, yeah, 60 seconds in a minute. Where do I want the seconds? I need the seconds on the bottom. So I'm going to put the 60 seconds on the bottom. I'm going to put the 1 minute on the top. Now why is this important? Because my minute label cancels out. Okay, and now I know that I go pi On top, that's all that's left, radians. And then 10 times 60 is 600. So I go pi radians in 600 seconds. And a lot of you are going to be like, oh my goodness, I don't know what this is. Well, if it makes it even easier for you, you actually can divide pi over 600 and get a super small number. And that's how many radians you go in 1 second. And that's a lot of times what we like to do. But for right now, we're going to leave it kind of as that. So let's kind of look at this scenario. So I kind of gave you the quick idea using the Ferris wheel. Now we're going to go through a bunch of other ones. If I ask for angular velocity, you need to find this formula on your salmon sheet. Plain and simple. Okay? And we're going to base it off of radians per unit of time. That's what we want to push towards for angular velocity. So here's an example. If I give you a point on a circle rotates 3 pi over 4 radians in 3 seconds, I would like to know the angular velocity in radians per second. Okay, so I see angular velocity as what I need as an answer. So instantly I should say omega equals theta over t. I know my angle is 3 pi over 4. Okay? Divided by my unit of time in this problem given to me was 3 seconds. Okay? And now I got to try figure out how to actually divide that. It's kind of like the Titanic 2-deck thing. I know you guys don't like me saying that, but this is like 3 over 1 on the bottom. So I can multiply top and bottom by 1/3 to cancel it out on the bottom here. Okay? So I end up getting what? 3 pi on top, 12 seconds on the bottom, and we end up reducing it down to pi over 4 radians per second. And once you get done doing that, is my label on the bottom what I want? I asked for radians per second, so I'm good with this. So that would be my simplest answer. So if I give you the radians as 3 pi over 4, it's nice because I give you the radian measure for theta, and then I gave you the time in seconds, which is what we were looking for. So I didn't have to convert anything at all on that one. Okay? Here's where it might be a little bit different. Let's say a point moves 60 RPMs. Now, you car people, anything else involving engines, this is relatively easy for you. If I say RPM, what's the R stand for? You want to say this is revolutions per minute. Okay, 1 revolution per minute. So instead I actually said it's 60 revolutions in a minute. Alright, so what we need to do now is give angular velocity. So let's kind of back up. If I need to go and give me the actual formula that I need to answer the actual question. Angular velocity, the omega, is theta over time. Theta needs to be in radians. I gave you 60 revolutions. That's like starting on this spot on the circle and going around 60 times. Okay? So 1 revolution, we said 1 time around the circle was 2 pi. So how many radians is that? Alright? So that's what you need to figure out first. So I need to try to figure it out as times 2 pi radians. So I can say now that I have 120 pi radians in 1 per minute or in a minute. Alright? And that's what you have to do. That's it. Because this one's really simple because I gave you 60 revolutions in a minute and I want to know the angular velocity in radians per minute. So the only one I really had to change was go from the revolutions to radians, and I did that in this step right here. So I now have radians on top, and I have my unit of time, which was given in the problem as minutes, on the bottom. So my angular velocity, my omega, would end up being 120 pi radians per 1 minute. Alright? So that's using angular velocity. I feel like this is pretty easy because it's not overly complicated because you just need your angle in radians and your unit of time on the bottom. What gets a little bit complicated and what freaks everybody out is linear velocity. And the reason that we get freaked out is because there's so many different formulas that you can use. If you actually look at your salmon sheet, we've placed 2 of them on there. We've placed this one, and then we have also placed this one, Alright? We have not put this one on here, even though that it also is one that we can use. Alright? So we need to just try to realize is what actually is linear velocity. Okay, if you think about a circle, all it means is that if you're here and this thing's traveling to there, I want to know how fast we go. So what it does is this involves arc length. So if you actually think about this formula that we have first, linear velocity, which is v, velocity to linear velocity, equals S stands for the arc length. Your arc length over your measurement of time. That's how fast you're going. Okay, basically you're finding a rate. Okay, distance equals rate times time. Okay, and you're solving for your rate, the distance, which is your arc length, over your time. That's what we're finding. Now, where does this formula come from? If you look at your arc length formula, arc length is your radius times your angle. Okay, and that's what that comes from is you just substitute instead of S, your R times your theta. Okay, that is arc length, your radius times your central angle divided by the unit of time. And then where does the third one come from? What is theta over time? If you look at your angular velocity, theta over time is your angular velocity. So what we have is the same formula, just substituted out with different things that we can find. So another way to find it is your radius times your angular velocity. The reason this gets difficult is there's so many different ways that I can give you the problem, or the book can give you the problem, that you gotta really grasp this understanding to figure out which formula would be best suited for each specific problem. So let's just go look at an example and let's see if we can talk it out. So we have a circular saw blade. Radius is 5 inches. Okay, so that's important. Rotates at 600 revolutions per minute. And it says find the linear velocity on the point on the outer edge of the blade in inches per minute. Okay, so since I give revolutions per minute, okay, the common one that we're going to use, the one that we'll use more times than that, is just going to be your radius times your angular velocity. So we go back to what we felt, or what I feel was the easier concept, the angular velocity. Can you find that? Now remember, angular velocity is radius times your, I lied, that's arc length. Angular velocity is your theta over time. Alright, are you able to actually calculate your theta in radians? Now our angular velocity is 600 revolutions per minute. So I have the time, but I don't have radians on top. I have revolutions. How did I figure that out on the last problem? I need to multiply by 2 pi to figure it out in radians. So 600 times 2 pi is 1200 pi per 1 minute. Okay, so that ends up being our angular velocity. Now why is that important? All that tells us is the angle that which we have traveled. What we need to do is figure out our distance. Well, I need to times it by my radius. So I now know that my radius, which I said before was 5 inches, and then all you need to do is dump in your angular velocity in radians per minute. So these problems do get semi-complicated. Alright, so I have 1200 pi radians per 1 minute, times it by 5 inches. So that ends up being 6,000 pi inches in a minute. Now the radian label goes away when you multiply by anything with significance as a label. Okay, it's just a neutral label. It's not going to affect anything. So I have 600 pi inches in 1 minute. Alright, and then that would be the answer for the first problem. The problem is, I also said let's convert that to miles per hour. So my miles per hour, okay, that gets very tricky because I already have inches. I need to get to miles. Yikes. Okay, so can we figure this part out? Let's go 6,000 pi inches per minute. Now let's focus on one label at a time. Let's go from inches into miles. So how do I get there? I know that there are, 12 inches in a foot. So I want to get rid of the inches. So I'm going to do that. So the inches cross out. That's my goal. I don't want feet though. So how many feet are in a mile? So I have 1 mile is like 5,280 feet. Why is that important? Now I can cross out the feet. And now on the top I have miles, which is what I want. Except now I only have minutes on the bottom, and I need an hour. So I'm going to times it by another conversion factor. 60 minutes, 1 hour on the bottom. Why is this important? Now my minutes cross out, which I need to have happen, so that I only have hours on the bottom. And then you just multiply it all out. So you go 6,000 times 60 times pi divided by 12, and you'd end up saying that it's 17.85 miles per hour. That problem is pretty neat. Okay? So that's how fast a circular blade is moving. Okay? If it goes 600 revolutions per minute and the radius is 5 inches long, it's actually traveling 17.85 miles an hour if you let that thing just roll down the street. Okay? So that is linear velocity. So let's kind of look at one more. Bicycle wheel radius is 13 centimeters. Okay? And it turns at 3 radians per second. Find the distance traveled point on the tire in 5 minutes. So before you worry about how far something actually traveled, I need to know the linear velocity, or how fast it's actually moving. Okay, so linear velocity is the radius times your omega. Do I have that? Do I have the radius for 1? And you should be like, yes, it is 13 centimeters. Do I have the angular velocity? Angular velocity, remember, is just radians per unit of time. Do you have radians per unit of time? 3 radians per 1 second. That works for me. That is your angular velocity. This right here. So I don't have to mess with it at all. I can literally just dump it in. So I have 3 radians in 1 second. So if I multiply that out, my linear velocity, how fast it's actually going, is 39 centimeters per second. Okay? But what do they ask you? They say find the distance. Oh my goodness. Distance is what? Rate times your time. So what we need to figure out is distance equals rate times time. What's your rate? Linear velocity is your rate. It's how fast it's going. So 39 centimeters per second is how fast it's moving, times, here's the rough part. I need to figure out 5 minutes. I have a second here. Okay? I can't just multiply it by 5 and get my answer. Okay? What we need to do is actually convert it to how many seconds are in 5 minutes. So we need to also multiply by conversion factor. That's why some of these problems get hard. And that's why I emphasize the labels in the last 2 sections. I need to be able to cross the minutes out and get seconds. So I actually need to multiply by 60 as well. Okay? So that is the hard part. You can't go 39 centimeters per second and just multiply by 5 minutes and actually get your distance. They have to be the same label. Okay? Because now my seconds can cross out. If I'm getting a distance, I need to only have a distance. So 39 times 5 times your 60 would end up being approximately 11,700 centimeters. Okay? So we use the linear velocity formula. We were able to dump it in straight out, but then the hard part to this one is when I want to find a distance, I'm going to find use my speed, which that's what linear velocity is, how fast you're moving, times it by that time, and then you're able to get your actual distance. So here's the fun one. I think this is kind of entertaining. So I want to know, we have the sun goes up, the sun goes down. The Earth rotates once every 24 hours. All right? I want to find the linear velocity. How fast is a person moving at the equator? Now we sit in our desk and we don't feel like we move at all. Well, how fast are we actually moving, with the Earth? And that's what's entertaining, how gravity can not allow us to feel this. So if I'm asking you to find linear velocity, all right, I'm telling you the radius of the Earth is approximately 4,000 miles. Now, I know it's like 3,963 or 92 or whatever it is, but we're just going to say 4,000 for simplicity's sake. And then, what's my angular velocity of the Earth? I say it rotates one full revolution, one time all the way around in 24 hours. One revolution in 24 hours. Well, I need what to do angular velocity? Angular velocity is theta or radians, so I need to times it by 2 pi. So that means my actual angular velocity for the planet Earth, reduced down, 2 goes into 24 12 times, would be pi over 12 radians in 12 hours. So pi radians in 12 hours. And what I need to figure out now I can dump that in. This is what gets hard again. I have it in miles per hour. I want it in feet in a second. The reason I want to do that is I want you to snap your finger, and that's how many feet you travel. And you're going to be astonished at how fast the Earth actually moves. Okay? So when I multiply this out, I now need to multiply and get my labels correct. So instead of miles on top, I want feet on the top. Okay? So I need to multiply by what? 5,280 feet in 1 mile. Why is that important? Now my miles cancel. So I have feet on top. But I need to get seconds on the bottom. Okay, I have hours right now. So I need to have 1 hour on top, but that's like 60 minutes. So that way my hours cancel. But I don't want feet per minute, I want feet per second. So now I need 60 seconds on the bottom and 1 minute on top, so the minutes cancel. So now I have a whole bunch of numbers, and you got to figure out what to multiply. So on the top, I need you to multiply 4,000 times pi times 5,280. And then you need to divide that by 12, and divide it again by 60, and divide it again by 60. And what you end up getting, approximately, according to my notes, is 1,535 feet per second. So in one snap of your finger, you go a quarter mile or more in a second. That's how fast the Earth's really moving. I think that's astonishing, even though we can't feel that. Alright, so that is the power of Mother Nature and planet Earth right there. I think that's kind of fun. So that is how you find linear velocity at the equator. So this is what we'll work on. We're going to work through a whole bunch of these problems over the course of 2 or 3 days. So please don't feel like you have to understand this right now. And I hope you all have a wonderful day.